Ladies and gentlemen, hello and welcome, coming to you not quite live from One Take Studios, where today, oops, I'm going to move my camera apparently, where today we are looking at piecewise functions, and these get to be interesting sometimes, alright, piecewise functions. So here's the deal. It is going to be a combination of functions. We're going to have more than one function pieced together, kind of like, shoot, I can't remember. Frankenstein. There we go. So we're going to make a Frankenstein function basically, and these are going to be driven by their domain, and I'm going to show you what I mean by that. Honestly, the best way to see these is just to dive right in, and so I have two examples that I'm going to work with us here. For starters, I actually have a third coming up in a little bit, but please do your best not to get distracted. I did put these side by side, so kind of keep them apart from each other. Alright, so we are here on the left first. This is our first example of a piecewise function, h of x. Where notice I've got two pieces, so multiple functions. One is 2x minus 1, so this piece is a linear piece. And the other one is x squared minus 3, so this is a quadratic piece. So this function is part line and part parabola. This, however, tells me my most important information to get things going. This is a comma right here. It could be the word if. I've seen both. X is less than or equal to 0. They are telling you, when you're picking your x values to plug into your function, if you pick a number that's less than or equal to 0, you're going to use this function. However, if you pick an x value that is larger than 0, you're going to use this function. So it is not a matter of plugging into both of them. You must choose one, and that's going to be based on the domain that you've got going on here. All right, so I'm going to go with, let's see. I'm going to do a little bit of color coding here to make it hopefully a little bit better today. I'm going to go -2, -1, and 0. So I'm going to start there. Okay, so -2. -2 is most definitely less than 0. So I'm going to plug it in here. 2 times -2 is -4, minus 1 makes -5. All right, so that's going to be a point on our graph. -1. -1 is also less than or equal to 0. So if I put a -1 here, well, that's going to be -2 minus 1, that's -3. And 0 also fits the category of less than or equal to 0. So if I put a 0 in this first one, 2 times 0 minus 1, that's going to be -1. All right, so that's great. That's great. Now, here's what I'm going to do. I'm going to continue on the other side with 1 and 2, but I'm going to switch colors, because I want you to see that now we are venturing into this group right here. 1 and 2 are both greater than 0. So now all of a sudden I'm ignoring the top piece, the top branch, and I'm looking at the bottom one. So what if x is 1? 1 squared minus 3. 1 squared minus 3 is -2. And 2 squared minus 3, let's see, that's going to be 4 minus 1, right? Oop, my brain shut down. 4 minus 3 is 1. There we go. There we go. So what will this look like? All right, well, for the second piece, the bottom half of this, I've got a point at 1, -2. So 1, -2, that's going to be right there. And 2, 1. For the top part, based on the numbers here, I've got 0, -1, and -1, -3. 1, 2, 3, and this would keep going at -2, -5. I guess I can put that over here, -2, -5, that'll work. All right. One piece is a line, one piece is a parabola. This piece is our line piece, and it happens wherever x is less than 0. Here's the x-axis, here's 0, here's less than 0. This is that first chunk. One of our two functions as part of our piecewise function. It's a line. That's where it starts, that's where it goes. What about a parabola? I've got 2 points over here. Those are not very parabola-y. There's a fun word for you. Tell you what, let's go a little farther here. Let's go to 3. What happens at 3? Well, again, 3 is greater than 0, so 3 squared is 9, minus 3 is 6, so 3, 6. 2, 3, 4, 5, 6. Well, now I can see a little bit more of the parabola. See, here's the thing. This is a function, but I want it to always have some sort of value. I don't want to have this gap that I've got going on between these right now. If I start here and I draw, I'm missing something between 0 and 1. So think about it. What are the values between 0 and 1? they would all be greater than 0, so I need this parabola piece to fill in. This is my personal recommendation here. I'm going to put a star next to this. I'm going to plug in the point wrong for a moment. 0 is what I consider to be my breaking point. I've got something happening less than 0 to the left. I've got something else happening greater than 0 to the right. What if I plug in 0 to the wrong piece of my piecewise function? This says x is greater than 0. What happens if I plug in 0 here anyways? This is going to be 0 squared minus 3, so that's negative 3. So what am I saying? I'm going to use this one to give me a boundary point right here. Notice that is an open circle. This parabola piece is going to start at 0, but I'm not going to actually include 0, because as soon as I include 0, I'm back to the linear piece instead. So this guy starts here, and now I've got something, that's not too bad. There we go. Boom, boom, and boom. There's my parabola. So I've got a parabola on this half, a line on this half, and no matter where I go, I have a value. This will even pass the vertical line test, because right here, that's closed and that's open, so this is a function, and that's how it works. So again, my personal trick is I take whatever that breaking point is, and I actually plug it into both pieces. But the one gives me a closed circle, and the other one gives me an open circle, the boundary, to keep going for the second half. All right, so I'm going to try the same thing over here. Again, just one more time, walking it through, making sure that we're okay with this. I've got a piece on the left, a piece on the right. Ooh, but this time left and right of what? Fascinating, fascinating. This is less than or equal to -1, and this is greater than -1. I'm going to actually put a nice little dotted line right here at -1. This is my breaking point. I've got something happening to the left of -1 and something else happening to the right. Here my breaking point was my y-axis, so that served nicely. This is going to give me a nice visual for what I've got going on here. So let's see, 2 to the x, that's exponential. So over here we've got something exponential. What are we going to plug in? Well, let's see here. Do I want to go? Probably not. I'm going to go -2 for a second. -2, -1. I'm going to start with those guys. So -2 and -1. Actually, I'm going to go back to my other color, though. I'm sorry. Keep some consistency for us here. All right. So -2 in blue and -1. So -2 is less than or equal to -1. So that's going to be 2 to the -2. 2 to the -2. Well, 2 squared is 4. The negative means it's flipped. That's 1/4. That's weird. Okay, and what if I have -1? Because again, -1 is less than or equal to -1. That's 2 to the -1. That's again flipping. That's going to be 1/2. Okay, so this is a bit strange. So at -1, I've got a value of 1/2. Ew. And a value at -2 of 1/4. How is that exponential? What do you see? Because this would be exponential growth, right? This would actually start here and swing up, and the x-axis would be an asymptote for this graph. So this piece is starting here and coming closer and closer and closer and closer to excuse me, the x-axis for all of eternity. So that's not really much of a graph piece. In fact, I'm going to move this just to give us a little bit more breathing room here. There we go. All right. So this is a little tiny exponential piece that's going to get closer and closer and closer to the x-axis. All right, what about the other part of this? Well, let's see here. Let me change my colors. Sometimes talking for a living has its effects. All right, so let's say I go 0 and 1, and let's start with there and see where it takes us. I'm sorry. 0 is greater than -1. So this is time I'm going to go for this one. So 3 times 0 plus 2 is going to be 2. And 1 is greater than -1. So 3 times 1 is 3 plus 2 is 5. So we're talking 0, 2, and 1, 5. 1, 2, 3, 4, 5 right there. Yes, okay. I know this is linear, but I also kind of like to know where that open circle is. Where's the boundary for this half? So again, I'm going to star this. This is not an actual point on the graph, but this is going to give me a boundary. I'm going to plug in the forbidden number -1 into the second one here. Even though this is greater than -1, I'm going to plug in -1 anyways. So 3 times -1 is -3, plus 2 makes -1. So that means at -1, I have a boundary right here, which makes sense for the line that we have going on here. That's our starting point, and this is going to kind of keep going like this. So the dotted line here is not part of my graph, but it does show nicely that I've got one thing happening to the left of -1 and something else happening to the right of -1. Piecewise functions, they're in pieces. Could you add a third piece? Yes. Could you add 12 pieces? I suppose, as long as you had a good reason, perhaps. But yeah, that is the idea. All right, so piecewise functions, we are Frankensteining together multiple graphs, taking a piece of each. Notice these will always pass a vertical line test. No matter where I put a vertical line, it will pass a vertical line test. These are still functions. All right, so keep that in mind. Last one, and this is, believe it or not, shorter and sweeter than it looks. This is called a step function. All right, what is weird about this one? It's got 3 pieces, but notice this just has a 1. Not a 1x, not x plus 1. This is a 1 and a 3 and a 5. And I just have single numbers. I decided to use the word if instead of the comma this time, just to give you some variety. You can use the word if, or you may use the comma. But again, it's driven by the domain, so the domain tells us where to go and when to do that. If I just said graph y equals 1, that would be that'd be a horizontal line. So this is going to be a piece of a horizontal line. The piece specifically where x is less than 2. Okay, so here's 2, 1, 2, and it's going to have a value of 1, but notice that's less than not equal to. So boundary, right here, we want this piece, for everything x is less than 2, we're going to be at a height of 1. That is our first step. Our next step is at a height of 3. Again, it's another little horizontal line segment in this case, because if you notice, this one goes from 2 to 4. So we got stuff happening at both ends. So here's 3, that's not a 3, there's 4. Notice what we've got going on. That sort of looks like a 3. Okay. Height of 3, 1, 2, 3. This is or equal to at 2. So this is going to be closed. So again, we see this closed, open, one of each, because one's taken over for the other. So this graph works right up until we hit 2, and then this graph takes over. And this goes all the way up until 4, but notice it's not or equal to 4, it's just a boundary at 4. So my next step is right here. At a height of 3, 1, 2, 3, I've got a piece. So this piece goes from from 2 on down. This piece goes from 2 to 4. This piece then goes from 4 on up, and this is at a height of 5. So 4, 5, there we go. So this piece now takes over at 4, and is at a height of 5, and greater than is going to keep on going like that. So that is the idea of a step function, is that we have a bunch of little horizontal steps. They might be evenly spaced, they might not, that's okay. But what you will see is oftentimes little segments for both, like you'll have open circle at one, closed at the other. But always keep in mind, it's got to pass the vertical line test where one is open, the other is closed, or one is open, the other is closed. This function works right up till we hit this point, then this guy takes over and keeps going. Alright, so these are a little bit weird. It is my understanding that they are a lovely calculus conception as well. So, yeah, play with these, it's worth it. Why did I draw these all up by hand instead of my calculator? You're not going to get the same understanding from your calculator. I'm sorry. I love my calculator. This is where the knowledge is going to come from. All right? Okie dokie. Have fun.